This video is about reducing fractions, converting mixed numbers to improper fractions, and fractions to decimals. So let's start by defining rational numbers. These are the set of all numbers that can be expressed as a fraction, like a over b, where a and b are integers, and the denominator can't be 0. So the numerator is what we call the top, the denominator is what we call the bottom of the fraction, and the bottom of the fraction can't be 0. A rational number is reduced to its lowest terms when the numerator and denominator have no common factors left other than 1. So a simple example of reducing a fraction would be like if you had 2 over 4, both of those are divisible by 2, so if you reduced it, you would get down to 1/2. And now the 1 and the 2, the numerator and denominator, have no common factors other than 1. So that would be a simple example of reducing or simplifying your fraction. Let's try one that's quite a bit more difficult. So we want to divide it by the greatest common factor that they have. In the previous example, it was a 2 and a 4, and the greatest common factor was a 2. Easy to see. With numbers like this, we might want to use our old trick for finding the greatest common factor of the two numbers so that we can be sure we're dividing by the best thing possible when reducing our fraction. So the method we used for finding greatest common factors between two numbers was to create the factor tree. So one way to make 130 would be to do 13 times 10, split the 10 into 5 and 2. And now I see the prime factorization is 2 times 5 times 13. Do the same thing for 455. I could split it into, 5 times 91. I could split 91 into 7 times 13. And then I can see the prime factorization for this. And now once I have the two prime factorizations written, I find anything that is common, like the 5 and the 13, right? And multiply them together. So 5 times 13 is 65. That means 65 is the greatest common factor between 130 and 455. So to reduce this fraction, if I divide both the numerator and the denominator by 655, I will get this fraction reduced to its lowest terms, which is going to be 2 over 7. So if you can figure out the greatest common factor, that's your magic bullet for reducing the numerator and denominator to its lowest terms. Let's try one more example. So we're going to try to find the prime factorization of 72 and 90. Do it a little bit more smoothly this time. So whatever occurs to you to break the number into, right, to get down to the prime factorization, now I'm down to prime numbers. I have 2 to the 3rd power, and I have 3 to the 2nd power. For 90, maybe I think of 9 and 10 first. That's the prime factorization right there, 2 times 3 squared times 5. And then I'm looking for anything they have in common. It looks like they both have 1, 2, and they both have 2 3s. So 2 times 3 times 3, which is 18. That's going to be the greatest common factor of 72 and 90. So if I set up the fraction, 72 over 90, divide both the numerator and denominator by 18, I'll get this thing reduced to lowest terms, which is going to be 4/5. Nice way to do it without a calculator as well. Mixed numbers and improper fractions. So these are just two different ways to express any fractional quantity that's more than one whole. So if you want to know that these two things are equivalent, we could do a visual, like the way you might have first learned fractions as a child would have been with circles. So 4 wholes and 1/2 would look like 4 circles all shaded in, and then 1 circle that's been split in half with only half of it shaded in. Well, another way to express that same quantity is by talking purely in halves. How many halves have been shaded? So if I split each circle in half but shade the same amount, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 halves. So 4 wholes and 1/2 is the same as talking about 9 halves. So that's the difference between a mixed number and an improper fraction. They're both used to express the same sort of quantity, a quantity greater than 1, but one with wholes and parts and one just talking about parts. So to convert, there's a shortcut you can use that's explained in the green box. I'm actually going to show it in a slightly different way for conceptual understanding. In this example, convert 3 and 4/5 to an improper fraction. I'd like you to think about the 3 as how many fifths that is. So if you had 3 whole circles shaded in, but each circle was divided into 5 pieces, and you were going to shade them all, you'd end up with 15 pieces shaded, right? So 3 as a whole number is the same as 15/5. Plus there's the 4/5 piece that's there as an extra little bit shaded, and so in the end, this is the same as saying 19/5. That's what 3 4/5 is as an improper fraction. If you wanted to apply the shortcut from the green box, it's to take 5, multiply it by 3, and then add that result to 4. I find people forget this shortcut or apply it in the wrong way and end up with some sort of crazy answer. But if you do indeed follow this shortcut, 5 times 3 is 15, plus 4 is 19, you will get 19, and then you keep the denominator the same. I just think it's much more conceptually helpful to imagine it the first way I showed. So here in the next example, convert 2 and 5/8. You're thinking, how many eighths do I have when 2 full circles are shaded in? Well, if there's 8 pieces in each circle and 2 full circles are shaded, that's 16 pieces overall that would be shaded. Plus there's 5/8 left over from this other circle. And so this would be expressed as 21/8 altogether. So I think it's more conceptually helpful to do improper fractions that way. Converting to a mixed number, so to go the other way, you'll just want to divide. So the instruction says divide the denominator into the numerator. And you may want to do this on a calculator. If indeed we divide 42 by 5 on a calculator, it's going to give us a decimal. But it's really the whole number part we care about. I want to figure out how many times 5 fits into 42, how many whole times. I know 5 goes into 48 times. So it goes in 8 whole times, and there would be 2 pieces left over, right? Because 8 times 5 is 40. So there would be these 2 little units left over. And so 2/5 is the fractional piece that's left over, converting it to a mixed number. So you do just want to divide, and then you leave the remainder over the original denominator, and that's going to be your mixed number. To talk about decimals a little bit, you might want to remember place value. Okay, so if you're going to read that first decimal out loud, rather than saying 0.7, which is what we would usually call it, the correct way to read that is 0 7/10, or 7/10. By reading that out loud as 7/10, because that's the location of the 7 on our place value table, that's the 10th place. By reading it as 7/10, you automatically can hear the fraction. 7/10, right? When you read it out loud correctly using place value, you're saying the fraction with your words. So the next one is 3 located in the 100th place. If you know that this is the decimal, you can read this table to figure out what place value you're in. So 3/100ths, right? When you say it out correctly, 100ths becomes the fraction 3/100ths, right? Or 3 over 100. Same thing with the next one, 8,000ths becomes 8 over 1,000. And then if necessary, these could be reduced to lowest terms. So here's some examples. It wants us to express these as a decimal. So this is converting from a fraction to a decimal rather than a decimal to a fraction. Here, you're going to want to use a calculator to divide this. So if you had a calculator out, the fraction bar is where your division symbol is, and you read from top to bottom. So if you do 3 divided by 8 on a calculator, it will convert it to a decimal of 3.375, or 375 thousandths. If you do 5 divided by 11, you will notice it's going to give you 0.454545 forever. It's a repeating pattern, which you could express with a bar over the repeating pattern, so a repeating decimal. And then the last thing to note here is that any rational number can be expressed as a decimal. The decimal is either going to be terminating or have a repeating block of digits. So as an example, there was this we just had on the previous slide. This is a rational number because it can be expressed as the fraction of 2 integers, like 3/8. Let's think of another example. 6 repeating. It's a repeating number, a repeating block of digits. In this case, just the 6 is repeating. And we know that this can be expressed as 2/3 or perhaps 6/9, however you think about it. And that is a ratio of 2 integers. The only sorts of decimals that cannot be expressed as a ratio of 2 integers would be something like 1, 4, 1, 5, 9, and then there is no pattern to it, right? Nothing is repeating. The next digit might be an 8 or a 3 or a 5. And so with no repeating pattern, a decimal that never ends cannot be expressed as a fraction. And so those are the numbers that we call irrational. There's no way to express it as a fraction of two integers. But decimals that terminate or decimals that repeat can always be expressed as a fraction.